Good morning, everybody. Today we have Jorge Casares. Jorge studied in Barcelona, but did his PhD here in the IAC. He defended in 1992, and then moved to the University of Oxford, where he did a postdoc of 4 years. He came back to the IAC in 1997, where he's leading the group on binary systems with black holes and neutron stars, and since 2005 he has a staff position. Today he will talk about one of these binary systems, a very interesting one. So Jorge, we can start.
Okay, thank you, Mar. Good morning, everyone. Well, today I will talk about a scientific result that we presented in Nature 1 month ago. And basically, we have detected what we think is the first case for a black hole orbiting a B star. And here you see the list of authors of the paper. The paper is the full list, apart from myself, includes Ignacio Negueruela from University of Alicante, Marc Ribó from the University of Barcelona, Ignasi Ribas from the Instituto de Estudis Espacials de Catalunya, Josep María Paredes from the University of Barcelona, Artemio Herrero and Sergio Simón from the HeII. Well, stellar mass black holes have been discovered because of the X-ray emission that is produced due to mass transfer in interacting binaries. The vast majority of these systems have been detected in low mass X-ray binaries. And they have the particularity that they are X-ray transients. Basically, what happens is that you have mass transfer from a Roche-Low filling star, and this mass is slowly stored into an accretion disk, and eventually this accretion disk undergoes mass transfer instabilities, viscous instability, and the matter gets accreted into the hole. And this produces dramatic X-ray outbursts, which are easily spotted by satellites. The key thing about these systems is that when they settle into quiescence, then it is possible to detect the companion star and perform radial velocity studies, and finally estimate the mass of the compact object. And this is, following this recipe, we have demonstrated that in 17 cases we have black holes, stellar mass black holes. Now, in addition to this, group of 17 X-ray transient black holes, we have also identified 4 black holes in high mass X-ray binaries. You see them in this sketch, in the top part of this sketch, and then basically they are black holes which are accreting matter from the wind of massive OB-type stars, and they are X-ray persistent, so they are X-ray bright and they are easily detected. One of them, there is only one in the galaxy, which is Cygnus X1, and the other 3 are extragalactic. There are 2 in the Magellanic Clouds and 1 in the nearby galaxy M33. But still, we haven't found a black hole orbiting a B star, and this is actually quite remarkable, because the big number, or the great majority of high mass X-ray binaries, they belong to the class of B X-ray binaries. Basically, they are neutron stars which are accreting material from the equatorial envelope, which is being ejected by a rapidly spinning B star. So we know about 80 systems in the galaxy, and in total is about 150 if we include those systems detected in the Magellanic Clouds, and they all have pulsating neutron stars. Now we think we have discovered the first B X-ray binary, which with a black hole instead of a neutron star. But interestingly, this has been detected not because of the X-ray emission, but possibly because of the gamma ray emission. In the same way as X-ray satellites changed our view of the universe in the late 60s and 70s, now Cherenkov telescopes and gamma ray satellites, they are opening new windows to the study of the universe. actually, these telescopes, they are starting to detect populations of objects which are emitting a large fraction of their radiation at very high energies, even at tera electron volts. In particular, there is a group of binaries, of interactive binaries, which are powerful gamma ray emitters. In order to produce gamma rays, you need to accelerate particles to relativistic speeds, and it has been proposed that this can be done either through inside a relativistic jet in a black hole binary, or as a result of the collision between the pulsar wind, a pulsar wind, and the fast wind of a massive star. So this produces a shock front where particles are accelerated, and there you can actually generate gamma rays through inverse scattering, Compton scattering of UV photons from the massive star. So actually, the group of gamma ray binaries is a pretty small number. We only know about 7 in the galaxy, and the great majority, they belong to the second group. They are pulsars, and the companion stars, they are in most of these cases, they are B stars. They are rapidly spinning B stars. The latest case of a gamma ray binary candidate was detected by the AGL satellite in 2010. It showed a short gamma ray flare, and within the 0.6 degrees error box of the satellite, there is a B star. The star is named MWC 656. It's a pretty bright star, and it was proposed to be the counterpart because it displays a photometric modulation with a periodicity of 60 days, 60.4. And it was proposed that this was the orbital period of this presumably gamma ray binary. So we started in 2011 doing a campaign on this B star. We mainly use the Liverpool telescope, and here you can see in the top figure the middle spectrum is the average spectrum of the entire campaign, and we compare it with the spectrum of another gamma ray binary, MWC 148, and the spectrum of a B template star. So you can, the spectrum is, it has classic B features like emission lines from the circumstellar envelope of the B star, mainly Balmer lines, and also some weak iron lines, iron 2 lines. Also, one thing which is remarkable is the extreme width of the absorption lines from the B star. Because of the large rotation, the absorption lines are very broad. So we estimate a rotational broadening of about 350 kilometers per second. So then we extracted radial velocities from these absorption lines, and we obtained a radial velocity curve, basically proving that the B star is indeed moving in an orbit, and therefore is a binary. So you see in the bottom panel the radial velocity curve of our photospheric absorption line radial velocities, together with the best eccentric fit model that we could obtain. Well, the large scatter that you see is actually illustrating how difficult it is to get radial velocity excursions of a few tenths of kilometers per second from lines which are as broad as 350 kilometers per second. So this is a strong limitation of the work. But in any case, we published a tentative set of orbital elements in a paper in Monthly Notices in 2012. But one thing that we didn't notice at the time was a tiny emission line which we mistook as one of the iron 2 lines. If I had a laser pointer, I could show you which one is. Well, it's one of the tiny lines which is around, it's actually helium-24686. It's a sharp line. So you can see here a close-up view of that spectral region with the line that we have identified is helium-24686. And this line is actually very remarkable because these lines are never detected in B stars. B stars, they are not hot enough to pump this transition in the B circumstellar disk. So that was weird. And so we one of the interesting features of this line is that it is double-peaked. So this is a signature of gas moving in a Keplerian orbit. And the other particularity of this line is that it is modulated with the 60-day orbital period, and it moves in antiphase with the helium-1 absorption lines. So this is telling us that this line is not coming from the circumstellar disk of the B star, but is coming instead from gas orbiting the companion star in this binary. So then we fitted Gaussians to this to the individual line profiles in order to trace the motion of the companion star to the B star. So now, in order to refine the orbital motion of the B star, we decided to fit the iron 2 lines, the double peak emission lines, iron 2 lines, which are coming from the B circumstellar disk, instead of the broad absorption lines from the photosphere. This color intensity diagram compares the evolution of one of the photospheric absorption lines on the left to one of the iron 2 emission lines that are produced in the circumstellar disk. So while the photospheric absorption lines, they are very broad, and it complicates obtaining radial velocities, the double peak iron 2 lines are actually is much more sharp, and so we decided to exploit the sharpness of this double peak, fitting double Gaussian models in order to measure velocities velocities for the B star. And these lines are known to be formed in the innermost part of this of the B circumstellar disk, so they are good tracers of the orbit of the B star. So we did, and we obtained on one hand a set of velocities from the companion star based on the helium-2 emission, and then another set of velocities from the B star, which were obtained from these iron 2 lines, which are produced in the innermost part of the circumstellar disk. So we perform eccentric orbital model fits to the two sets of radial velocities independently, and then we obtain solutions which have the same eccentricity, they have the same time of periastron, and also the argument of the periastron are in antiphase, which is something that you expect in the case of two stars moving around the same center of mass. So then we decided to fit the entire set of velocities using a single double line orbital model, and well, this figure shows the final fit, and on the table on the right hand side we list the final set of orbital parameters. No? The key thing here is the mass ratio. The mass ratio is extremely large. I mean, it's very large compared to the classic values that one obtains in B X-ray binaries. It's a factor 4 larger than you typically see. So now, in order to constrain further the nature of the companion star to the B star, we need to estimate the mass M1, which is the mass of the B star. To do so, we compare the spectrum of our B star with a set of templates obtained with the same instrumentation and the same spectral resolution. The closest match are provided by these two cases, a B1.5 giant and a B2 giant. To start with, the width, the narrowness of the wings of the Balmer lines is telling us that the luminosity class corresponds to that of a giant, no? Of a giant star. And then also looking at the relative strength of several metallic lines, we constrain the spectral type to be between B1 and B2. And actually, the comparison strongly supports a B1.5 giant star. So now we need to rely on the different calibrations available in literature in order to obtain a mass for this star based on this spectral classification. The most precise calibrations are given by detached eclipsing binaries. And actually, the closest example is given by this star B380 Cygni, which contains exactly a B1.5 giant, and the mass of this B star has been estimated to be 13.1 solar masses. But in any case, we decided to adopt a wide range of masses in order to account for the uncertainties that we have in spectral type classification, and therefore we take a mass in the range between 10 and 16 solar masses. And it should be it should be noted here that in any case our mass is probably a conservative limit, because it might be underestimated because of the large rotation. So this produces the star to look cooler and less luminous than it really is. So, and the factor it would be around 10 or 15%. So we are confident that this mass limit is very conservative. So now, to summarize, if we take our orbital solution, we find a mass ratio of 0.41. If we take our spectral classification, we get a spectroscopic mass of between 10 and 16 solar masses for the B star. So the companion star must have a mass between 3.8 and 6.9 solar masses. So the companion cannot be a main sequence star, because with this mass, it could be a B3 or B9 star, which would be easily detectable in our spectrum. It cannot be a subdwarf either, because these stars have typically masses between 0.8 and 1.3 solar masses. A Wolf-Rayet star should show very strong wings and high excitation lines which are not detected in our spectrum. And finally, this mass is too massive for a white dwarf and a neutron star. So the only alternative that we are left is a black hole. Also, incidentally, it should be mentioned that the fact that we detect a unstable accretion disk around the black hole is another indication that we are seeing something which is fundamentally different from the other class of B X-ray binaries that we know of. Because in none of the B X-ray binaries with pulsating neutron stars, a long-lived accretion disk have been detected before. No? So now to conclude, what are the implications of this finding? Well, it was a decade ago. It was basically proposed that, or it was defined that there was a problem with the lack of black holes with B companion stars in the galaxy, and so this is called the missing B X-ray binary, black hole B X-ray binary problem. And there are two possible explanations that have been proposed for that. No? On one side, it was proposed that basically these systems, they exist. I mean, black holes with B companions exist, but they are very difficult to detect because there is an observational bias. And then, on the other hand, it was proposed that they rarely form. I mean, there is an evolutionary bias which makes very hard for a black hole to survive the evolution, the binary evolution, and therefore the number of these systems in the galaxy should be very, very, very small. In the first case, basically the reason for the observational bias against detecting these hidden black hole B X-ray binaries is basically the truncation of the circumstellar disk of the B star. Models by Podsialowski and colleagues in 2003 predicted that these systems should form with short orbital periods and low eccentricities. And for this range of parameter space, tidal forces basically prevent the accretion disk, the equatorial disk of the B star to be transferred into the black hole, and therefore these systems would remain as quiescent forever, basically. So, but then on the other scenario, what we have is, as I said, there is a problem in the evolution of the binary, and basically systems which would form black holes with B companions. They rarely survive the common envelope phase in the binary evolution. They end up as mergers. And then only a few systems would survive, and the predictions are that the ratio between neutron star and black hole B X-ray binaries in the galaxy should be about 50. So we know about 80 systems, so the expected number of B with black hole binaries should be around between 0 and 2. So we have detected one. In principle, our detection confirms, or not confirms, but it is consistent with the prediction of this second evolutionary scenario. However, we think that this is probably not the case, because this system is relatively close. I mean, we estimate a distance of about 2.6 kiloparsecs, and also it's one of the brightest systems, B X-ray binaries, known. So it seems quite difficult, that improbable that we have detected one of the only black hole B X-ray binaries in the sample of 80 systems that we know already, no? And we think that one of the key properties of this system is the weakness in X-rays. These systems, I mean, we look at archival ROSAT images, and the system has a very low X-ray luminosity. We set up an upper limit of 2 times 10 to 32 ergs per second, and these luminosities are consistent with the X-ray luminosities that are seen in black holes in low-mass X-ray binaries during the quiescent stage. So this is suggesting that basically the accretion disk around the black hole in this system is in quiescence. Now, given the extremely low mass transfer rates typical in B X-ray binaries, the theory of mass transfer instabilities in disks predicts that these systems should have extremely long outburst recurrent periods. And basically we interpret this system as an example of this property. We believe that there might be more B X-ray binaries with black holes in the galaxy, but the combination of the fact that the system is this black hole is being fed with an extremely low mass transfer rate from the companion star, and the fact that we have a black hole and we don't have a solid surface re-radiating the accreted luminosity, implies that these systems are very difficult to detect in X-ray surveys, and maybe there are many more than predicted by models. And this is the conclusion. Thank you very much for your attention.
Thank you very much, Jorge. Time for questions. I cannot believe it. Come on.
So how do you propose detecting more of these systems in the future then? I mean, what can you do to try and...
Well, you see, this signature, the helium-2 4686 emission line, which is not detected in classic B X-ray binaries, is a clear signature. So maybe one simply has to go through all the catalogs of optical spectra of B X-ray binaries and classic B stars. Actually, classic B stars that don't emit X-rays is probably the best.
This is a very naive thing, but this helium line, I mean, it appears in Wolf-Rayet stars. Could you tell us again how do you know that this is not, I mean, the companion is not a Wolf-Rayet star?
Because
you get these high excitation emission lines in Wolf-Rayet. I mean,
in Wolf-Rayet stars you have very broad, not only helium-2, but high excitation lines. And here we only see a narrow double-peak helium-2 emission line. So, I mean, where are the other high excitation lines that are typical of Wolf-Rayet stars? There is another argument against Wolf-Rayet stars, and is that we have also looked at the spectral energy distribution in the UV, And we find that the spectrum is fully consistent with a B star of that spectral type without any excess. So if you could have a Wolf-Rayet star, you would expect an excess in the UV that we don't see.
I guess the luminosity of the B star is too high that the veiling is not playing a role. Veiling in the let's say accretion disk of the black hole. And the other thing would be if it is interesting to have to get a high resolution spectrum of this B star to be able to get a better estimate of the mass.
Yes, well, the spectrum I showed is a spectrum of obtained with the Mercator telescope, which has a resolving power of 80,000. So this has a pretty large resolution. The limitation here is the broadness of the photospheric lines because of the very fast rotation. So this complicates obtaining a more precise spectral classification based on fitting model atmospheres. No? But we think we can do that. We will try to do that and compare at least that the stellar parameters that we obtain by fitting models are consistent with the spectral classification.
What is the magnitude of this?
8. It's a pretty bright object, yes. Yes, and yes, the other question, yes, you are absolutely right. I mean, the luminosity of the B star dominates completely the spectrum, and so there is no veiling from the accretion disk.
Okay, if there are no more questions, then we can thank Jorge again